Welcome students, and I am Ravi Shankar. See, today we are going to study about the work done. In the last video itself, I have given a small introduction regarding the work done, and we have defined the work done is given by the formula work done is equal to F into R into cos theta, or we can say this work done as F cos theta into R, that is the perpendicular component of F multiplied with or taken with the displacement. Or we can say that the work done W equal to F into the perpendicular component of the displacement. So for doing the work, the SI unit was being given as joule, and we have studied the dimension as m L square T power minus 2. Regarding this small introduction regarding the work, we have studied in our last class. See, today in this class, let us go on with two concepts. One is how a work is said to be done with a constant force. And the second one, how work can be done with an variable force. So, first of all, let us consider like this. What is the work done by a constant force? How you can able to calculate work done by a constant force? So, let us consider an object on which a force is acting, and the force that is acting on the body is taken to be constant. The applied force never changes. So that constant force produces a small displacement called to be dr. If the displacement produced is small, that is dr, then the work done is also taken to be a small work done taken as dw. Let us consider. So in order to study about the work done by a constant force, let us consider like this. See, a constant force F, a constant force F act on a body or acts on a body, so that it can able to produce a small displacement. So a constant force F acts on a body so that, let us consider a small displacement, a small displacement, and that small displacement considered as dr. So a small displacement dr is produced by the force on the body, is produced by the force on the body. So for producing a small displacement of dr, what is the work done? Let us take like this. Let the small work done, or let us consider, let the work done on the object or work done on the body by the force is work done on the body by the force. Let us consider that as dw. If work done by the on the body by the force is dw, then we can write the force dw equal to the component of force which is perpendicular. So the perpendicular component of the force, that we are calling it out as F cos theta multiplied it with the small displacement dr. So let us take that small displacement is dr. If you want to calculate the total displacement by the constant force acting on the body from one initial position to final position. See, in order to calculate the total work done, so let us calculate the total work done in displacing the body, in displacing the body, from initial position, from the initial position. Let us take this initial position as Ri to the final position, to the final position. Let us consider that final position as RF is given by or is calculated as is given by. So now I am calculating the total work done W in order to displace the body from the initial position Ri to the final position Rf. So what is the total work done? Let us consider the total work done as W. So we can take the small work done that was being done as dW. This total work done can be calculated by integrating this small work done between the two positions, initial and final. So integral of dW from the initial position Ri to the final position Rf, which can be written as integral of Ri to Rf. What is dW here? In the above equation I have written, that is F into cos theta multiplied it with dr. Here F cos theta is a constant. So the very constant forces acting on it. The only quantity that is varying is displacement. So integral of Ri to Rf of dr. You just integrate this dr. What is the final answer that you can able to get? Then the work done is given by F into cos theta multiplied it with, when you are integrating dr, you can able to get r within the limit Ri to Rf. So on applying the limits, we can able to get the answer as the total work done F cos theta into Rf minus Ri. So using this formula, we can able to calculate the total work done by a constant force. See, we can represent this total work done by a constant force with the help of what? By a graph. So we can calculate or we can represent the work done by the constant force by a graphical representation. So we can write the graphical representation is given by the graphical, okay, the graphical representation is given by graphical representation. Graphical representation is given by. How you can able to get this? See, on the you are having the y-axis. On the y-axis, let us consider the constant force that is available. So on the y-axis, I have taken the component of force which is perpendicular, and the other one along the x-axis, I have taken the displacement dr. In this displacement, I have taken two positions. One is the initial position Ri, another one is the final position Rf. See, when I am considering the force to be constant, then the constant force acting on is represented by a line parallel to that of the x-axis, because the force is taken to be constant. It is not varying. Now you drop two perpendiculars, one from R1 and another one from R2. So you can able to get an area enclosed by this graph. So the area enclosed by the graph between the force and displacement will be giving you the total work done in displacing the body by the force from the initial position Ri to the final position Rf. So we can get the conclusion that, what's the conclusion? So we can say the area enclosed by the graph between force F and dr gives the work done by the constant force. Since the force is considered to be constant, you can able to get the force equation, or the force is represented by a line parallel to that of the x-axis. This we are calling it out as the work done by constant force. Now, the next one. What is the next one? The same concept, the same work done we are going to study. But we have to take that the applied force is taken to be a variable. Either the applied force or the direction along which the force of application, both any one of the component can change. If that is the case, then we are representing it as the work done by the variable force. So the next topic that we are considering is work done by a variable force. So the applied force is considered to be not a constant. The applied force is taken to be a variable. So let us take like this. When a component of variable force, when a component of variable force, F, let us take that variable force as F, acts on a body, then a small displacement is produced. A small displacement, a small displacement is produced on the body, and that small displacement produced on the body is represented as dr. Okay, for this small displacement, for this small displacement, for this small displacement, let dw be the work done. So same concept what I have written there, I have written it here. The only change is force is considered to be a variable, not a constant. So let dw be the work done. Okay, if dw be the work done, then it is given by the expression dw equal to f cos theta into dr. When you are considering f cos theta into dr, here we are saying that F, the applied force, as well as the angle between the application of the force and the displacement theta are considered to be what? Are considered to be variable. So what is the total work done then? Then we can say the work done, or we can write like this: the total work done is equal to W. That the total work done W is equal to integral of dW from one position to another position. Let us write like this: Ri to Rf. But here we can't integrate. We will be putting it in numerical. In solving numerical problems, we can apply Ri to Rf. Instead of this dW, I am taking it as f cos theta into dr. This is taken to be what? This is taken to be the expression for the total work done that was being available by an variable force. Here also we can apply an graphical representation. So a graphical representation is given by a graphical representation. A graphical representation is given by. What is that graphical representation? You see, on the y-axis, we are having what? On the y-axis, we are having the component of force, F cos theta. And along the x-axis, let us consider the displacement. Here we have taken two positions. One is Ri and another one is Rf. Okay, one is Ri and another one is Rf means, so in this case, the force is considered to be a variable one and not a constant one. The force may vary as it's as like the whatever may be the force that is acting. We can't able to say in an regular manner. For example, initially the force is considered to be at this position. Within it reaches the final point, the force may increase or force may decrease like this. So you drop two perpendiculars, one from Ri and another one from Rf. So this line that I have drawn here is an variable force, and the two perpendiculars, one at RI initial position and another one as RF the final position. So the nature of the graph is can't be an regular shape. Now here also the conclusion is the area that was being enclosed by the graph inside this will be giving you the total work done. So what is the conclusion arrived? Here also we can say the area enclosed by the graph, the area enclosed by the graph gives the total work done, total work done by the variable force, total work done by the variable force. This is, we are calling it out as that work done by the variable force. A small difference. In case of a constant work done, since the force is considered to be a constant, the work done we can able to get it out in an the area of the graph bounded is a regular shape. But in this case, in variable force, it won't be in regular shape, one thing. The second thing, in case of work done by a constant force, we have integrated the displacement and given the equation as F cos theta multiplied with R2 minus R1 or RF minus R1. Here in numerical problems, we will be applying how much amount of variation is being caused. According to that, we have to integrate and solve the problems. So, hope you should have understood the work done by a constant force and work done by a variable force. With this, the topic regarding work done is over. Based on this, we are having some 5 or 6 example problems, and let us go through that example problems one by one. Okay, let us go on with the example problems. First of all, the first example problem 4.1. Come on, let us go with the first problem. The first example problem that we have to study here is example problem 4.1, which is said to be available in the page number 169. So you just take your book and go along with the problem as I am reading with it. A box is pulled with a force of 25 Newton to produce a displacement of 15 meter. So a box is pulled with a force of, so the force acting on the body is considered to be 25 Newton. How much displacement it has produced? The amount of displacement produced is dr, which is equal to what? Which is equal to 15 meters. Then if the angle between the force and the displacement is, so they have given it out as theta, considered to be 30 degree, and you are asked to calculate work done. This problem may be asked either in one word or in 2-mark question. See, direct substitution. As you know, the work done W is given by the formula F into dr into cos theta. You substitute for this. What is F? F is considered to be 25 Newton. Displacement is considered to be 15. And here it is cos theta. So you can write cos 30. What is the value of cos 30? Cos 30 is given by root 3 divided by 2. So you substitute and simplify. You will be getting it as 25 into 15 into root 3 divided by 2. How you can able to multiply this 25 into 15? You can get the answer 25 into 15, 5 into 5, 25, then 2, then 10, 10 plus 2, 12. Okay, then here when you are multiplying with 1, you will be getting it as 25. So 5, 7, 3, 375. So you can get 375 into, what is root 3? 1.732 divided by 2. On simplifying this, I can get the answer as 324.78. Here it is work done. Work done measured in terms of the unit called to be joule. So work done is given by W equal to 324.78 joule. This is the first example problem example 4.1 in page number 169. Hope you should have understood this. Let us go for the next example problem. Problem number 4.2 in the page 170. So you take down the page number 170 and let us move on to the next problem. See, we are going to study about the example problem 4.2 set to be available in the page number. What is the page number? Page number is considered to be 170. Come on, take to page number 170 and go with the problem number 4.2. An object of mass 2 kilogram falls from a height of 5 meter to the ground. What is the work done by the gravitational pull or gravitational force on the object? Neglect air resistance. Take G equal to 10 meter per second square. Come on, go with the problem again. An object of mass 2 kilogram. So let us consider the mass of the object m is equal to 2 kilogram falls from a height of. So the amount of height that it has coming down, that is the displacement. If you want to write it as h, write it out as h, or if you want to write it out as dr, consider it as dr, and that value we are taking it out as 5 meters. Okay. Then what is the work done by the gravitational force? So work done is asked. Then G is given. Acceleration due to gravity is given as 10 meter per second square. Since it was being given that work done by the gravitational force, you calculate the gravitational force F. What is the gravitational force? Gravitational force is nothing but m into G. So F equal to, what is m? M is 2 kilogram. What is G? G is 10 meter per second square. So I can say the gravitational force F is equal to 20 Newton. If you want, you can say Fg, since it is gravitational force. If you want, you can put it out as F into G, or in general, you can write it out as F. Now, what is the work done? See, we know that work done is given by the formula Fg into cos theta multiplied it with dr. Here, theta is considered to be what? Here, theta is equal to 0. So, cos theta is equal to 1. Why theta is 0? Because the direction of motion as well as the direction of gravitational force are acting along the same direction. So, I can say Fg is 20 Newton into cos theta 1 multiplied it with dr, it is 5. So I can consider 20 into 5 as what? 20 into 5 as 100. 100 joule is taken to be what? 100 joule is taken to be the work done by what? Work done by the force. Isn't it? Any difficulty? So the work done by the gravitational force is taken to be 100 joule. This is problem number 2, simple problem. Let us move on to the next one. Problem number, example problem number 4.3 in the next page. That is in the page number 171. So let us consider. What is the problem? The problem is example problem. And that example problem is example problem 4.3. And this example problem 4.3 is available in the page number 171. Come on, take down the problem and go with the problem. See, an object of mass 1 kilogram is sliding from the top to bottom in the frictionless inclined plane of inclination angle theta equal to 30, and the length of the inclined plane is 10 meter as shown in the figure. Calculate the work done by the gravitational force and the normal force on the object. Assume the acceleration due to gravity G is given as, we can say that 10 meter per second square. See, first of all, let us consider a diagram. So the diagram given is an inclined plane. So when you are considering this inclined plane, okay, the angle of inclination is considered to be what? The angle of inclination is taken to be or considered to be 30 degree. Okay, then a mass of 1 kilogram is sliding from the top to bottom in the frictionless inclined plane of inclination 30. Okay, now on this inclined plane, a object is being placed. That object is having a mass m, and the mass of the object m is given as 1 kilogram. Okay. The length of the inclined plane is considered to be what? The length of the inclined plane is considered to be 10 meters. So let us take like this, from this end to the other end. So this we are considering it as the length. This length L, it was being given that length L is the displacement produced on the body. Let us consider it as 10 meters, which is the distance or the displacement moved by the body. Calculate the work done by the gravitational force. So first it was being asked as work done by the gravitational force. Okay, work done by the gravitational force and also by normal force and also by the normal force. So these two we have to calculate. First of all, let us calculate case 1. The case 1 is the work done by gravitational force. Work done by gravitational force. This work done by gravitational force, I am saying it as Wg. See, I have to consider what is this work done. This work done is nothing but I am stating the general formula F vector dot dr vector. Now, F vector dot dr vector means what is the component of force acting along the inclined plane that I have to consider. So, I am considering the diagram now. When you are taking the diagram, the vertical downward force or the vertical downward gravitational force acting on this mass is nothing but this mg. The normal force acting is, normal is drawn perpendicular to that of the plane. So let us consider the normal force drawn as M. If you are dropping or if you are extending this normal force on the other side, so the direction of the normal force on the other side is this one. Now you resolve the that is, you resolve the gravitational force Fg, that is mg, into two components. So the angle between the normal and the vertical force acting is represented as theta, which is equal to angle of inclination. When you are resolving mg, this mg can be resolved into two components. One of the component is taken to be the adjacent component and another one the opposite component. The opposite component is acting along what? The opposite component is acting along the inclined plane, which is the perpendicular component of mg, which is responsible for taking the body from the top of the inclined plane to the bottom. So the component of mg, which is acting along the inclined plane, is the opposite component. So opposite component is mg cos theta. Then the adjacent component is parallel or along the normal force, and that adjacent component is mg. Opposite component is taken to be what? Opposite component is mg sin theta, not mg cos theta. We have to consider it as what? We have to consider, because it is opposite. So we have to consider it as mg sin theta, and the adjacent component is considered to be mg cos theta. So we can write the force, the gravitational force mg. Mg is taken to be the gravitational force. This gravitational force mg is resolved into two components. Resolved into two components. See, the component which is along the inclined plane, along which the work is said to be done. So I can say along the inclined plane, along the inclined plane, the component of force is F sine theta, or I can write Fg sine theta, or I can consider it as mg sine theta. And along normal, along the normal force, along the force, or I can say along the normal force, the component is Fg cos theta, or I can write it out as mg cos theta. But what we are asked to calculate the work done by what? The work done by the constant force. So work done by the constant force is Wg, which is F dot dr is the force or the component of force which is perpendicular multiplied it with, or perpendicular component of the force multiplied with the displacement. Perpendicular component of the force, gravitational force, is mg sine theta multiplied it with dr. What is that dr? Dr is the length of the inclined plane along which it was in motion. So what is m into g? M is 1. What is g? G is 10. What is sine? Sine 30. Multiplied it with the 10. So work done by the gravitational force is equal to 10 into 10, it is 100. Multiplied it with sine 30. Sine 30 is 1 by 2. So we can say the work done by the gravitational force is considered as 50 joule along what? Along the inclined plane. This is what we are taking it as what? This is what we are taking or considering it as the work done by the gravitational force along the inclined plane in order to move that body from the top of the inclined plane to the bottom. Then let us go for the case 2. Hope you should have understood this. What about case 2? You look at the diagram. So let us consider the case 2. What is case 2? Work done by normal force. Work done by the normal force. What is the work done by the normal force? See, the normal force, while it is considered to act perpendicular to that of the inclined plane, no displacement is produced on that direction of force. So the direction, since there is no displacement, or we can say the motion of the body is perpendicular to that of the normal force, no work is said to be done. See, the work done by the normal force is given as no work is said to be done. No work is said to be done by the normal force. By the normal force. Why? As the direction of motion, as the direction of motion is perpendicular to the force or perpendicular to the normal force. Since the direction of motion is perpendicular to that of the normal force, no work is said to be done because theta becomes 90. If theta becomes 90, we can say work done W or Wn. F cos theta into dr. Theta becomes 90 means theta cos 90 is equal to 0. So the work done by that normal force is equal to what? Work done by the normal force is equal to 0. This we are taking, or this we are considering it as the problem number 4.3. Okay, problem number 4.3. Okay, you can see the whole problem here. Problem number 4.3 available in page number 171, isn't it? So by resolving the gravitational force, we are writing the value for the component of force which is acting perpendicular to it, the perpendicular component of the force multiplied with the displacement. So along the displacement, what is the force acting? That is mg sine theta. Don't get confused with f cos theta into dr. For that, I have written the formula. Because of that only, I have written the formula as Wg is equal to f vector dot dr vector. Hope you should have understood that. Okay, so let us move on to the next problem. That is the problem number 4.4 in page number 171. Come on, take your book. Come on, go with the problem. Example problem number 4.4. If an object of mass 2 kilogram is thrown up from the ground, reaches a height of 5 meter and falls back to earth. Calculate the work done by the gravity when the object reaches a 5-meter height. Then the work done by gravity when the object comes back to earth. Total work done by gravity both in upward and downward motion, and mention the physical significance of the problem or the result. Okay, what it is given. If an object of mass 2 kilogram, let us consider the body of mass m, and the body of mass m is equal to 2 kilogram, is thrown from the ground, reaches a height of, so the displacement made, let us consider it as r, as 5 meter. It falls back to earth. Neglect the resistance. Take G. Neglect the resistance and calculate. Let us consider the value of G as 10 here also. G is equal to 10 meter per second square. Let us take. What is the first concept asked? The first concept asked this: work done by the gravitational force in the upward direction. So A is work done by the gravitational force in the upward direction. In the upward direction. So that work done, let us consider it as W. What is that W? Work done W is equal to, we can say the formula as, in general, we can say the formula as F cos theta into dr, magnitude. Instead of F, I can say, since it is the gravitational force, it is mg cos theta multiplied it with dr. What is theta? Here, theta is the body is thrown upwards against the gravitational force. The gravitational force is acting in the downward direction, but the movement is along the upward direction. So I can say theta equal to 180 degree. If so, I can write cos theta. That is, I can get the answer for cos 180. Cos 180 is -1. Take this and substitute it here. So the work done W equal to, what is M? M is 2. What is G? It is 10. Here cos 180 is -1 multiplied with the amount of displacement produced. It is 5. So on multiplying 2 into 10, 20, 20 into 5, it is 100 with -1. So minus 100 joule is the work done by the gravitational force in the upward direction. Here we have to focus our attention regarding the angle. Then option B, what is the second one? The second one asks us the work done by gravity when the object comes back to earth. So work done by gravity when the object comes back to earth, comes back to earth, comes back to earth. What is that work done? W. The same concept. See, let us consider F cos theta into dr, which is equal to mg into cos theta into dr. Here, what is the value of theta? The object is moving in the same direction as that of the gravitational force. So theta equal to 0 degree. Therefore, cos theta is equal to cos 0 equal to 1. Now, what is the work done then? Work done is equal to, what is the value of m? It is 2. G, it is 10. Cos 0, it is 1. And displacement again 5. So the total work done is considered to be what? The total work done is considered to be 100 joule. But here the 100 joule is considered to be positive because along the direction of force, we are having what? We are having the displacement. So we have calculated the work done by the gravitational force in the upward direction as well as in the downward direction. What is the third concept that was being asked? You are asked to calculate what is the total work done in both upward and downward motion. So the third one is, so option C, the total work done is asked. Total work done அப்படின்னு சொல்றது, let us take like this. W total is equal to work done in the upward force plus work done in the downward force. So work done in the upward force plus work done in the downward force is the total work done. Since work done is a scalar quantity, the scalar sum or the algebraic sum of the two work done will be giving you the total work done. So in the upward direction, it is considered to be minus 100, plus in the downward direction, it is considered to be 100. So we can say, what is the total work done? The total work done is equal to 0, or I can say it out as 0 joules. So finally, when you are considering the net work done, the net work done is, we are saying that the net work done is equal to 0. Then the next one, what it is asked, it was being considered, it was being asked the physical significance of the result. So what is the physical significance? So conclusion. So we are going to write the physical significance of this. The physical significance, it implies that the result implies that we can take like this. The result implies that the gravity does not transfer any energy to the object. That the gravity does not transfer any energy to the object, since the total work done is taken to be what? The total work done is taken to be 0. Isn't it? This we are calling it out as the problem number 4.4. Hope you should have understood this problem. Let us move on to the next problem, problem number 4.5. Come on, go with the problem number 4.5. See, a weightlifter lifts a mass of 250 kilogram with a force of 500 Newton to a height of 5 meters. See, a weightlifter of mass. So mass of the weightlifter is considered to be 250 kilogram. How much force he is applying? The force that he is applying is considered to be 5000 Newton, and is lifting it to a displacement R as 5 meter. So what are the things asked? The first concept is work done by the weightlifter. So the first one is work done by the weightlifter. Then what is the second one asked? The second one is what is the work done by gravity? So the second one is work done by gravity. What is the third option or third question asked? What is the net work done? Okay, let us consider these three. So let us take the first one. What is the first one? You are asked to calculate work done by the weightlifter. Direct formula. Work done by the weightlifter. What is the work done by the weightlifter? Let us take like this, WW, work done by the weightlifter. So work done by the weightlifter is the force acting on it, the component of force F cos theta multiplied with the displacement produced, either dr or r. See, the force and the displacement of the weight lifted, both are acting along the same direction. So we can say theta equal to 0. If theta is equal to 0, then cos theta equal to 1. Therefore, work done by the weightlifter is equal to F into R. What is the force acting? The force acting is 5000 Newton. How much distance he has moved? He has moved it to a distance of 5 meters. So you will be getting the answer as 25,000 joule. Or we can write like this, 25 into 10 to the power of 3 joule. Or the answer may be 25 kilojoule, taken to be the work done by the weightlifter. Okay. Then the next one. What is the next one? The next option or the next question asked is work done by gravity. Work done by gravity. So let us take this work done by gravity as W of G. The formula is F cos theta multiplied it with the displacement dr. Here, the gravity is pulling in the downward direction and the object is lifted in the upward direction. So here, theta is equal to 180 degree. If theta is 180 degree, then cos theta will be equal to -1. So work done by gravity is equal to minus of F into dr or F into r. So minus of F is 5000 into dr is considered to be again 5. So minus of 25,000 joule. Or I can write minus of 25 into 10 to the power of 3 joule or minus of 25 kilojoule is considered to be work done by what? Is considered to be or taken to be work done by gravity. The negative sign indicates that the displacement is made against the direction of action of the gravitational force. This is the second one. Then what is the third one? The third one that has been asked is the net work done on the or the net work done by the lifter. What is the net work done? So let us consider WT, total net work, is equal to work done by the weightlifter, work done by the weightlifter plus work done by gravity. That is the net work done. So the total work done WT is equal to WW plus WG. This total work done, this is one is 25, another one is minus 25. So the net work done or the total work done by the weightlifter is equal to 0. Hope you should have understood this. See, one more problem. Let us go or let us study it with the help of the variable force. Come on, let us move on to the next problem. So we are going to the problem number example 4.6 and page number. It is available in the page number 173. Come on, go with the problem. A variable force F equal to kx square acts on a particle which is initially at rest. Calculate the work done by the force during the displacement of the particle from x is equal to 0 to x is equal to 4. Assume the force constant K is equal to 1 Newton per meter square. So what it is given, a variable force is given. So F is equal to kx square, which is initially at rest. So Ri is equal to 0. Calculate the work done by the force during the displacement of the particle from x. They have given the displacement as x. So x is equal to, or xi is equal to Ri is equal to 0 to final position xf, or I can write as we have studied it in our theory as final position rf, which is equal to 4 meters, and the value of the constant k is equal to 1 Newton per meter square. So you are asked to calculate what is the work done. We have to calculate. See, it was given. F they have given, xi xf they have given. So work done W is given by integral of. In our theory, we have studied it as Ri to Rf. Then we will be writing f cos theta multiplied it with what? F cos theta multiplied it with the dr. Or we can write this in general as Ri to Rf as force into displacement. Here the force is along the x-axis, Fx into dx. Then I have to put this as xi to xf. So what is this? W equal to integral of xi to xf. What is f of x? F of x is given as kx square, and amount of displacement instead of dr, I have written it as dx. So substitute and simplify. When you are taking this kx square dx, integrating k cannot be integrated, so k is taken out. When you are simplifying this x square, when you are integrating x square, you will be getting the answer as x cube divided by 3 within the limit xi to xf. So I can write the value of k as 1, taking this 3 outside, 1 by 3, then x cube within the limit 0 to 4. On simplifying this, you can get 1 by 3 into x. That is, you are getting 4. Or we can write 4 to the power of 3. So 4 to the power of 3 is 4 cube, which is 64. 64 divided by 3. If you want, we can simplify. So here 2, here 1, then 10, 3, 3, 3, 3, like this it is going on. So the work done is given by the answer 21.33 joule. This is the work done by the functional force that was being given as F is equal to kx square. So with this, in this lesson, which is divided into 3 concepts: work, energy, power, we have completed that first topic called to be work or work done. All the theories as well as all the example problems have been worked out or solved. So focus your attention on this and try to complete it on you try to complete the topics on each and every day. Okay. Thank you from Ravi Shankar.